Welcome back, everyone. It's a delight today for only the second time in our show's history to be talking about all things wind. I know very little about this topic, so I'm super excited today to have Neal Rickner from a company called Airloom in the US here to talk about it. And we're going to talk all about Airloom later in the show. We always start with the problem space, but even before we get to that, Neal, welcome to the show. And I want to understand both a little bit about you and your background, but also how you came to be working on this problem of wind before we dive in.
Yeah, well, thanks for having me. I really appreciate it. I started my career as an F-18 pilot in the U.S. Marines. I spent 12 years active duty flying fast, then transitioned out of the military through business school at Columbia, and then I was at Google and Google X for about a decade. Just given where you're recording, I would be remiss if I didn't mention that I spent a little under a year as a study abroad student at Monash University in Melbourne, which was pretty fantastic. And I drove actually the Oodnadatta track all the way up into Uluru and then back across to the Gold Coast. And that was a fantastic journey. So I miss it there, and I'm envious in many ways. So military, business school, Google, and it's really at Google where I learned how to work on energy, in and around energy. And I started connecting dots with my time in the Middle East. I was a Marine. I was in Iraq 3 different times. I was in Iraq because of energy and learned just how central energy is to our security, and sort of became an energy security nut. And then while I was at Google and learned about energy from a commercial perspective, got to really understand and appreciate energy as the key to our prosperity. And so I put those two things together. Energy is our prosperity and our security, and it's sort of where I'll spend the rest of my career.
Got it. Okay, wonderful. And I have a few other follow-up questions on that, but I think I can come back to them later. I want to just connect the last dot there of working in and around Google. Were you working on energy projects at Google? Because people don't typically think of Google as an energy company, but that's probably, it helped me understand that a bit more.
Yeah, I was at Google X. I was not on the energy team. Believe it or not, actually, Google does have an energy team where they work on, like, they invest in and manage the assets they invest in, wind, solar, storage, etc. But I was at Google X working on technology. As a part of that, I worked on smart grid and batteries and a wind energy company called Makani. That was actually airborne wind technology. And in that role, we were developing wind projects and doing it was sort of, think of it this way, as entrepreneurship, where it was building a company, but from inside Google. And we got kind of the best of both worlds, where we didn't have the sort of normal risk for a startup founder. We had the benefits of being in a big company that was safe and secure, but got to work on really cool advanced tech.
Yeah. And like, what prompted the move to kind of you spin yourself out of that and go and focus on Airloom full time?
Well, I had been in that ecosystem for about a decade, and it was just, I mean, at that point, it was just sort of long enough. I mean, I will also note that it was 2021. It was the middle of the pandemic. I had been living up in the Bay Area, and my family, most of my close connected family, was down in Southern California. So it was a bit of it'd been a decade. I was ready to go see some new things and do some new things, spread my wings a bit, if you will. And then also, during the pandemic, move close to home.
Yeah, love it. Okay, a little bit of push, a bit of pull, and a bit of what's shiny object and green grass over there. Awesome. So let's go straight into wind generated power, because look, I think, and I'll speak for myself here, but I think I'm speaking probably for a broader mass of people. We tend to think of wind generated power as these massive turbines that keep getting bigger and bigger, and typically offshore, but some of them onshore as well. Certainly in California, there's tons of them onshore. I want to understand kind of what the status quo looks like with wind generated power, kind of how we got here, and what are the problems or gaps with the status quo?
Yeah, so people have been generating energy from the wind for a long, long time. I mean, think about the Dutch back in the 17th century. I mean, it's been a long road, mostly for milling, low wind speeds, et cetera. The modern era of wind really started in the late 80s and early 90s, when we were able to build more sort of 3 to 5 bladed turbines. Actually, I should say 2 to 5 bladed turbines that were on the top of a tower. Um, we were building metal blades back then, but over time we figured out that we could build uh, variable pitch blades that were more efficient, and then variable speed rotors that were even more efficient. And in the course of the 90s and early 2000s, you really got to a point where you could produce really, really low cost energy. There were a bunch of other types of wind that were tried during that era. Vertical axis turbines, which really is an axis that points straight up out of the ground, and the blades spin around that axis. But after many, many different things were tried, what was ultimately the winner of that was the three-bladed turbine on a horizontal axis. So horizontal means sort of parallel to the ground with the three blades spinning around it. Maybe a misnomer, but I would say that 95+% of turbines have been deployed onshore. There's really only one part of the world that's been widely built offshore, and that's in the North Sea off the coast of northern Europe, between Europe and Norway. And the reason for that is that building a big horizontal axis turbine offshore, if you can put that turbine into the seabed floor, you're basically building an onshore turbine offshore. You just put it into the seabed floor that way. There are some unique ways to anchor it, but building an offshore turbine in deep water is really, really expensive. One, it's a big, tall tower. It's really heavy, and therefore you got to build a big floating foundation. But two, that turbine has to be basically upright within a few degrees, and therefore that foundation has to really be massive to hold it basically straight up and down. So floating offshore wind, there haven't been very many of those projects built at all. There have been, a few. Everything that's been built has been, not everything, but most of what's been built has been built up in the North Sea in Europe. 90, as I say, 95+% has been built onshore. But that predominant architecture, for a while we thought we could do two blades, but really everybody's building three-bladed horizontal turbines now.
Yeah, and like I kind of painting that picture, and thank you for clarifying on the stat as well. I think, as you said, it is a misnomer. We tend to think of, like, even in Australia right now, they're trying to go through and put some wind turbines in, and they're putting, it's all the arguments are about these ones that are about 20, 30 kilometres offshore, to my understanding. But the main game is still onshore, which makes sense, a hell of a lot easier to do. What are the challenges with that setup? Like, are we running out of places to do it, or is this the cost practicality is not working? Like, what's wrong with wind today, I guess?
Yeah.
Or limiting it?
Look, I'll start by saying I'm about to say a bunch of negative things about horizontal axis wind turbines. I should start by saying how much good there is in that technology. I have a lot of friends that started from the very early days back in, when as I said, in the early 90s, companies like Kenetech and Zond Wind eventually became Enron Wind, acquired by GE. There's a whole history here of very smart people building really, really great technology. Um, what it started with was if you think about the basic physics and how you get to a design that is both robust, because the wind is angry, as I like to say. The wind is not a steady. It's not a steady flow, right? The wind, as you know, if you just stand outside, it's blowing all over the place. Well, a machine has to react to all of that, which is why I say it's angry, because you have a cyclic load, and these turbines are just out there spinning all day, every day, and it looks like they're going slow because they're massive, but really they're doing freeway. The tips of those blades are doing freeway speeds around the circumference. So these are fast moving, heavy things that are massive and have to stand up to the test of time, 20, 30 years, in a really, really harsh environment. So, look, we've gotten to the place we are because of really smart people building robust systems that acknowledge that really harsh environment, and then built systems that could last in those harsh environments. But with it, there's a but, which is that, look, what has been built because of the way that system works, it's driven us to building larger and larger systems. And I like to say we've sort of painted ourselves into a hole, in a way, into a corner, because how do you keep going? How do you keep getting bigger? And we're now at a spot where if you're not delivering 100+ meter blades for every wind turbine, you're just not capturing the economics that make these projects profitable. And so, part of what I learned at Google X, as you really dig into the details, is that that scale drives you into all sorts of absurdities. One, the example that I like to cite, and this is, really insider stuff, which, you have to be a wind person to appreciate, I guess. But I'll take you down this path, which is, I was in Texas, where most of the U.S. wind turbines had been built, at a project, and was just doing a tour. And I was like, so, this park has been built out of 1.5 megawatt turbines, but I read in the book that their GE 2.3 is way more efficient. Why are you still building parks with 1.5 machines? And they said, well, the downstream supply chain is all built for the 1.5s. If we were to try to change to the 2.3, it just wouldn't make any economic sense. And that, just like, my head exploded. I'm like, wait a minute. So you've got a way better machine. It's like far more, like, the device itself is far more technically efficient, but you're not using it because the trailer, you'd have to redesign the trailer for the crew to bring the new blade out. You'd have to, the guy who's been putting up your 1.5 machines would have to go buy a new crane. The road, anyway, you see where I'm going. There's all these sort of externalities that didn't get factored in. And that started me thinking about, what I say now is that, it's the device. Certainly, you've got to build a really efficient device, but it's all the stuff that happens around it. Do you have to widen the roads? Are you able to go to the most efficient or the most powerful winds, given that, like, you can't get some places with a gigantic wind turbine? You just can't get there. There isn't the road and bridge infrastructure to go there. And then you dig further and you're like, well, wait a minute. Why aren't there big wind turbines built in, the global south? And the answer is they don't have the port infrastructure, the roads aren't big enough, they don't have the cranes, etc. And you see what I mean by these externalities don't get factored in when you go to this scale.
Yeah, I mean, it's interesting as well because, like, if you think about in the last 10 years, there's the emergence of wind and the emergence of solar as kind of the driving force in renewable energy production. And solar is exactly the opposite. It is a very small thing that is just being made millions and billions of times. And we've got very good at doing that. And its price has come down because the scale has got big, but the actual individual device is small, which solves or avoids all of those issues. When you were talking before about infrastructure, like, I don't know how much of an urban myth it is, but that awesome story about the Cape Canaveral and the ruts in the road connected to the size of the horse's butt connected to the train line. You're familiar with this,
Yeah,
presumably?
yeah. It's
I'm just
yeah.
going I just want to indulge people who may not be aware of it, but this idea that two horses side by side, created a wagon of wheels a certain width that created ruts in the road, which is what they based the train lines on, which is therefore the size of the tunnels for the train lines. And they couldn't make the containers for petrol or for the gas for the rocket ships any wider than the tunnels they had to ship them through. And so the thing that went to the moon was influenced by the size of a horse's butt. As you said, it's absurd.
It's absurd. But I mean, look, you get, this is how engineers are trained, and I think rightly they focus on the requirements. What does this thing have to be able to do? How big can it be? Look, I think it's all based on sound engineering, but I think when you take a step back, and that's really what I was enabled to do by being at Google X, really take a step back and think about things in a different way. Yeah.
Yeah, and so let's kind of pivot from there because I think what we're sort of articulating is that there's nothing fundamentally wrong with wind, but if we want to 10x the amount of wind that we've got, then we're hitting up against not necessarily physics constraints, but where can we put these things? How do we get these things to where they are? How do we install them? And nothing to do with the fact that the machine won't work when it's larger. It's just that all the other things become a hell of a
Yeah.
lot harder, probably exponentially or logarithmically harder. So let's reverse into that. Like, where are the untapped opportunities in grid scale wind? So not just someone having one in their own home.
Yeah, I mean, first, I will start with there were very good reasons why the engineers back in the 90s dismissed the vertical axis turbine or some version of another kind of device, and part count or complexity of device, or look, the wind blows higher at higher altitudes, and then if you're really looking at the math, that the difference between the wind at a 50-meter hub height and a 100-meter hub height is not great, but not meaning not a big number. And the coefficients there are, 0.08 or maybe a 0.14 or something like that, small. But the power in the wind, which is to say the energy in the wind, increases with the cube of the wind speed, and exponents are powerful. So the amount of power in the wind between 50 meters and 100 meters is actually pretty substantial. So you're incentivized to go high. Again, this is why the decisions were made. But again, there's the but. I'm like, I can acknowledge all of the reasons why the existing industry did what it did. But there are substantial, I think, if you look at how, for example, a new wind turbine is designed. GE spent about $500 million making their current wind turbine a little bit bigger, and they'll only ever make a few hundred of that machine, and they'll have to go back through that design process again. And it's made out of specialized materials. It takes a long time to assemble. It's a very complicated, and so the opportunities. The reason I go back to that is because the opportunities are, as we see it, as I see it, is there a way for wind to have its sort of 2.0 moment? And I'll previous by saying, solar has gone through a bunch of iterations. You noted solar. Gas just went through an iteration where we thought we were at peak gas in the United States, and then we figured out fracking. And then look, here we are with a whole new opportunity. Geothermal is going through a similar kind of 2.0. And I think wind has a 2.0 if we can, if we go back, now that we've got technology that's different than the 90s, right? Than the early 90s, what is it that we could use differently? We started asking about, the major detractors are the height of the machine. There's a bunch of sites you can't build because it's just too tall, because of the size of the individual components as they're shipped, because that means you can't go on certain roads, and cranes are really, really huge, gigantic, right? And then lastly is cost. How could you build something that was really, really dirt cheap? And so we started with the cost one, actually, and what we said was, actually, if we could go back to Model T industrialization, which we say is start with super common materials, right? Readily available materials made into simple, robust parts at high volume. That's what we call Model T industrialization, light industrialization. Then what would that wind turbine look like? How could you make a wind turbine out of the sort of in a modular, scalable way that was lower in height, in a repeatable fashion that could be shipped in a container and didn't require cranes? And so that would necessarily, as I say, open up siting opportunities. One, because if you can build at low cost, you've got more potential places. Two is if you can unmoor yourself from roads and open up those lower those sites with height restrictions, that just gives you a bunch of places to go where conventional wind can't go. So anyway, that was the starting point.
Yeah, and what's quite interesting there is I'm sure you had some ideas as to how the thing would physically look, and I want to talk about the design in a little bit. But you've almost started from a place of let's give ourselves a design character, to take a kind of a Twitter approach. You've got 160 characters, work out what to say, not work out what you want to say, and then try to back solve later. And I think that's a really interesting kind of design paradigm. Some of yours were basically existing, straightforward materials or everyday materials. Site a design that could work in a low-rise site that could be reached by a pretty ordinary truck or maybe a basic semi, but certainly not specialized equipment, that didn't need potentially didn't need dedicated foundations to work with. It could be worked with an existing structure. Sounds like it as well. One of the constraints. Any other key constraints?
We hoped for that, but I don't. That actually ended up not being possible. We are going to have our own foundations, and I think. I get this question a lot. Could we build it on the top of a skyscraper? And there's a bunch of reasons. Actually, the wind is angrier on the top of a skyscraper, so
Yeah.
that
That's a
doesn't
good.
turn out to be good. But let me pause here for a second and say, I think important here to give a big shout out to the founder of Airloom. I am not the founder. I'm a hired CEO. I was at Google X in 2015-16 timeframe when the founder of Airloom, his name is Robert Lumley, went to a conference where my company, my Google X company, was presenting. It wasn't me, but somebody from my company was there. And he went to that. We were all sort of in the boat of like challenging existing wind turbines. He went to that conference, saw what we were doing, and said, "That is great. It's better physics. Like you're leveraging physics that have more efficiency, but it's too complicated. You need to take all of that physics and put it on the ground, make it simpler." I was in the process of learning that lesson. Like I would have, when I say that, what I mean is like if I had met Robert in 2017, 2018, I probably would have argued with him. Like we were right and he was wrong, but he was right. I'm going to say full throated at this point. He was right because what we were working on, we were trying to get some like get rid of the cranes, get rid of the complexity. We were doing some of this, but ultimately we had the wrong architecture. We've now jumped into this. I left Google in 21. As I mentioned before, I did some other stuff for a couple of years. Joined Airloom in 23, so a couple of years later. So all that is to say, I think I had started some of the conversations. I won't parse out which ones which, probably not that interesting. But I'd started some of this, like what could you do if it was simpler, robust material, common materials, etc. And then put it down for a couple of years and picked it back up with Robert's design, which was even further along this sort of simplicity, accessibility track.
Mm. And why don't we use that as a segue into the design? Because if someone looks at a photo, there's going to be links to this, so we'll either bring them up or add in links. But
Yeah.
just for people who are listening to it or just watching me gesticulate with my hands, help us understand what this thing looks like and what it's doing and how it works down to whatever level of technicality you'd like to go to.
Yeah. Well, technically it is a wind turbine, but it looks more like a roller coaster than a turbine. It is in the shape of a Olympic running track, so it's technically a stadium shape, although most people say it looks like an oval. It is on towers that are, say 20 to 30 meters tall. We don't call them towers; we call them columns because individually they don't do anything. And we want to differentiate ourselves from a conventional wind turbine. So the columns, go around the shape of the track, and on the top of those columns is a track. So think about a sail and a sailboat. Wind comes in from the side, drives the sailboat forward. In the same way, wind comes in from the side of the Airloom and drives those wings forward. And collectively, they pull like a mule chain on that belt. And then that belt is driven through a set of vertically oriented rotary motors. The wings are all attached to the same belt. So wind comes in from the side, drives the wings forward. The wings pull on that belt. They all pull collectively on that same belt, and the belt drives the vertically oriented rotary motors. This is just a cylinder motor that sits at the four corners so we can manage belt tension. And the belt, as it passes by, drives the single spindle at the top of that rotary motor. So it's super simple. Wind pushes the wings pull the belt drives those
Okay,
motors.
and so I'm going to definitely, when we do this on the video, at least put a visual up. And if someone's just listening on their phone and without the visual, I'd say just Google Airloom. You're going to see a photo of one on the homepage. But one of the questions that I've got,
Yeah.
which is, if you think about like, you take like a kid's toy, the thing where it like has 3 or 4 different wings on it, and they're all connected to one central kind of hub, and you blow on it, and the whole thing spins, and you're effectively blowing into all 4 of them. It's just that it's spinning, and each one's kept turning in front of you. So it's kind of like that, except that instead of being on a singular pin with 4 wings around it, they're actually on a ring. They're like on a, as you said, a stadium ring. I'm trying to understand, like, why have the sails on the stadium loop rather than just on the individual hub? What's the advantage of having them kind of spread out more?
Yeah, the advantage is what you want in wind energy generation is a big break up against the wing. The bigger, the better. We call it swept area. The reason is in horizontal turbines, it's a disc, and that area is the swept area of the disc. And so this is again sort of ties back to the conventional design. If you want a bigger swept area, you need to build a bigger foundation, a bigger tower, a bigger gearbox, and each of the blades has to get bigger. For Airloom, our additional swept area is just another section of rail, another post, and another wing. So we're adding swept area in a rectangular shape. The surface area of that swept area is what matters. How many square meters of swept area do you have, and what does it cost you? And that's really for Airloom, that's the key factor that is our advantage, is that we're making that swept area is about half price, given that we're not building a gigantic tower, all of the stuff around it that I mentioned before. We're building swept area, which is how you make money. You're building that swept area
Right.
for
So
half
if you had to
price.
draw, like, a swept area is a leading indicator for cost per, like, levelized cost of energy production. Is that what you're saying, essentially?
It is. It is. There's more to that story, as I mentioned, and this is, I think, the critical uh, sort of piece that investors, when they finally figure out this, because this is when they're ready to dive in, is that they're like, yeah, but isn't the wind stronger up at higher altitude, and isn't that V cube law really powerful? And I say yes, 100%. But if you look at the difference between the wind speed, meaning you take in all the factors, I'll simplify it this way, to say the difference between the amount of energy in the wind at 100 meters versus 30 meters, it's about a 20% reduction in total power. That's the first way you measure dollars in the wind, right? It's how much energy is in there in the wind. But if we're making swept area for 50% of the cost, that's how we outrun that equation. That's how we
Yeah,
outrun the
totally
rethink.
understood. And then I've probably got other technical questions, but the other main one that I have is if you visualize this, it's like the wind's coming from this direction and it's pushing on the sail, and the sail goes around the track and catches all that wind and drives some generators on all four corners of the stadium. And then it comes down to this side. What's it doing to not be going into the wind? Is it turning? Like, what's
Yeah.
happening?
Well, think about it this way. This is one of the disadvantages of this architecture. You need a sort of unidirectional or bidirectional wind, right? A conventional wind turbine will yaw into the wind, right? So if you have an omnidirectional wind, you can kind of adjust to that. There's a bunch of caveats there because wind farms, the horizontal axis wind farms, are built such that if you do have an off axis wind, you end up with a bunch of wake losses in the rest of the farm. But let's set that aside for now. For Airloom, what you want is the broad side of Airloom exposed to that main direction of wind. And what you find is that most of the windy places in the world, and this is really something, if you're not a wind person, that isn't readily apparent. We don't build wind turbines near people because people don't usually live in really windy places. So a low wind site is 7.5 meters per second average wind speed. That's what, give or take, but about 15 miles an hour average, not like once in a while, but like throughout
Right,
365
windy.
days, 7 days a week. It's really windy all
Right.
the time. That's right. That means it's blowing 25 half the time and 7 half the time, but whatever, you get my point. It's really windy. Those places are often unidirectional or bidirectional. This is why Airloom seems like, if you really think about it from that perspective, like, well, the wind's moving around all over the place. Well, in where you live, that's totally true. Where I live, that's true. But for most really windy places, it's pretty unidirectional. Or as I say, if it does flip around, it'll flip all the way around to the other side. Now, but you want, the reason I say it that way is, think about a sailboat. The sailboat goes across the frontage of that one wind direction. As it goes around, it's actually doing just what a sailboat does. It tacks to go the other direction. So our wings are all variable pitch, which means that they'll adjust to get maximum power output. So if we're dealing with a wind that's 50 degrees off our axis point, we actually adjust the angle of attack so that it's still producing maximum energy. And then when it turns around the other way, it actually flips around like a sail in a sailboat to do that same optimization on the
Interesting.
other
Okay,
side.
so it's essentially got an optimal downwind and upwind speed if you kind of take the sailing analogy, and hopefully the wind's coming directly from behind it and it's got its full spinnaker open. I'm going to keep going with the sailing analogy and using all of that power and then optimizing the other way on the way back through the turn.
It's not using a spinnaker. A spinnaker actually takes like wind from behind it and pushes it forward. We're using aerodynamic forces here. Think about In fact, we've studied the America's Cup sailboats, land land sailors, ice sailors are all using the same idea. It's like a windsurfer, essentially. It's how do you take wind from off? Like 90 degrees off is great. How do you get that and turn it into forward thrust? We're taking that aerodynamic force and creating forward thrust. Airplanes take that and create lift with it. We're taking that lift vector and pointing it forward. So that lift vector is actually driving the wind
Understood.
forward, wing
And so,
forward, which is
like, not
technically
that I'm
thrust.
scratching around for analogies, but I find it's when you have a new concept, it can be easiest to understand, to map it to one, to something that exists. Like, what would you say this is most closely aligned to? Is it a sailboat, like a windsurfing thing, or a plane, or is that probably the best analogy?
Yeah. Closest to a land sailor. I mean, this is actually sport for some folks. But yeah, a sailboat, land sailor, ice sailor, those are all. We look at those because they're taking a sail and they're trying to figure out how, compared to the wind speed, how fast can you go? And really, for us, faster is generally better for us. A sailboat's like four times the speed of the wind, meaning wind comes in at a certain speed this way, it goes four times. And that's like pretty aggressive. America's Cup, four and a half times. You know, ice ice boats are getting close to six and a half, seven. We're going to end up somewhere in the middle, but we definitely want to optimize. That's where you know you've got great aerodynamics, minimal drag, and a minimal amount of sort of wasted energy. But clearly, ice sailing is lowest drag because like there's no wheels, etc. But that's maybe the
Yeah,
clearest
perfect.
analogy.
Okay, cool. Let's switch gears from the product and the engineering because it's clear that if you put these things and it costs exactly the same amount to get one or the other out, the large existing wind turbines would probably have some kind of advantage, at least in the places where you can put them, notwithstanding all the other challenges. But when you start to talk economics, this is where the whole game changes from Airloom's perspective. So help me understand some of the factors that we spoke about. I want to understand materials, I want to understand fabrication and like assembly, and I want to understand transport and installation.
Yeah. We don't know yet if, in fact, what you said before. I presume that we're going to get to a place where horizontal axis turbines and heirlooms are deployed on the
Wow.
same site because landowners are going to want to maximize energy production, and there's no reason why you couldn't build both at the same time. The top of our blades are about at the bottom of where those their blades bottom out, right? So there are scenarios where that's true. There's also, as we talked about with floating before, there's opportunities for heirloom to go. We're about half the mass of a horizontal turbine on a per megawatt basis. So there's opportunities there too. But to answer your question about materials, we're 95% steel and aluminum. And that means you can source it from just about anywhere, right? I mean, every place, United States, Australia, et cetera, you can get steel and aluminum and you can get it at very low cost. Um, our manufacturing process, we're actually by design, and sort of go back to sort of first principles, we set out to design a system that was a very few number of parts, unique parts. And so we're 58 unique parts in the current design. Compare that with a horizontal turbine that's
I was hoping you'd have that number.
1,500
Thank
unique
you.
parts.
Wow, that's significant.
Yep. Yeah, it's a massive step change. And I think this is how we get to ridiculously low cost. The answer is like, how do you get to 50% of the cost per swept area? The answer is that you're building those simple, robust parts out of very common materials on an automated production line. The cost of those parts is basically the material cost plus a small margin. So think about that. And then secondly, this is where light bulbs really initially went off for me is to get the massive parts from a wind turbine plant to where they're meant to go is a very complicated, heavy industrial transportation uh, network, and that network is very expensive because you move a couple of blades and then you don't need to move blades and you have to create a special trailer and blah blah blah. So with heirloom, you just put everything in a container and into a worldwide shipping network that's already like bottom of the barrel cost. Everything goes in a container. You know that containers are cheap. Then you put things up with forklifts, right? I learned this the hard way with my Google X project too. We got to a scale where we needed a crane, and like mobilizing the crane was like $50,000. You're like, wait, what do you mean? Like I only need the crane for like 2 days, but well, it took the crew a day to put the thing up. So yeah, it's $50,000 because it was all this. So all of that is to say it is way lower cost to make. We're not using specialized materials. We're not doing one-off processes. People don't believe me when I say it, but there are parts in current wind turbines today that are, no kidding, literally made by hand. It's 2025 and you're like, that can't be true, but take yourself to a wind turbine plant. So we're making super low cost parts. We're transporting them in standard transportation networks that are super low cost, and then we're putting them up with very low cost, like a forklift that you can buy for 15,000 brand new, not a crane that you have to mobilize and rent over a period of time. Yeah, there are other things too that are hidden. For example, almost everywhere you have a big wind farm, you have to widen the roads. If you've got a county road, I don't know if it's one horse's butt or two, but
Probably four.
but you do have to almost always, and at least the ones that I've been a part of. And there are little things like that that just that make the device itself is expensive. Getting it there is expensive. Putting it up is expensive. But the site and the site development is also expensive. And with Airloom, you cut down on each of those things, get easier and easier.
And like, there's got to be a point in a graph where kind of, I'd say that there's kind of, standing existing wind turbines, and there's kind of this, diminishing returns in terms of the, I don't know, levelized cost of energy. Is that kind of the gold standard of how you compare one to another? And,
yeah.
And where are you at on that curve?
That is our ultimate metric for sure. That, I mean, at the end of the day, I am a capitalist. I also learn from my mentors at Google X that if you want to make an impact on the world, you got to build something that people are willing to pay you for. And so I am like, that is the ultimate metric is what does the LCOE come down to? And LCOE is fraught with all sorts of assumptions. You've got to make an assumption of what is the site? What's the wind resource at that site? And I can tell you if it's a class 1 wind site versus a class 3 wind site, the LCOE is going to change. A class 1 wind site is a 9.5 meter per second average wind speed versus a 7.5 meter per second average wind speed. So, but all of that put together, what we have modeled out, and we now have a full set of models that show that we can produce for low cost. We will produce energy such that we're going to get to an LCOE that is way lower cost than horizontal axis turbines, among the lowest cost energy of any type, whether it's solar or combined cycle gas, et cetera. And I can say that with some caveats. One is that we haven't operated at megawatt scale yet. We've operated at kilowatt scale. 2, all models are wrong. Some are useful. We built our model with, a healthy dose of humility, knowing that, we're going to put in margin where we think it makes sense, and we're going to hold ourselves accountable to intellectual honesty there. I think, but look, it's our modeling gives me a lot of confidence that even if we're pretty wrong, we're still going to have a very low cost source of energy generation. We also, there's some things we absolutely have to get right, and some things that are not maybe totally obvious with this new architecture. And I'll go back to the sort of horizontal axis turbine industry that you mentioned before, of like, is there, they discounted some of these architectures like what Airloom is doing because of the part count. The exposed parts. Well, you're going to have lots of dust. You're going to have lots of ice. What do you do if the wind shifts very rapidly? I think we've learned from the last 30 years of those hard lessons learned. We've applied the IEC standard, which is the sort of when things break, they put it into the IEC standard, so the rest of the industry doesn't have to make the same mistake again. And so we've applied all of that knowledge that has been gotten over the last 30 years Two, we think to address those challenges. But I'll give you one really simple example. We've got a couple of guys on the team that have been building roller coasters for about 20 years. And there's this really simple example, and it's just one of a couple of examples, but I like it because I think it sort of gives you a sense of what we're up against. He says, look, we've been dealing with these wheels for 25 years. We've used them on thousands of roller coasters. I know they work, but on roller coasters, we make sure that the track is pretty level. If you've got a lip in that track and that wheel has to go up and over the lip every turn, it's going to go da-dunk, 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 da-dunk. And that wheel's going to run, that's going to wear out in like 6 months. And our economics are destroyed if we have to replace our wheels every 6 months. Like, that's not going to work. We're making an assumption that we have to replace the wheels every 5 to 10 years. And he says, look, if you can make that rail relatively level, it doesn't have to be perfect, but within a certain level of tolerance, and you get rid of that da-dunk, 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 totally fine. 5 to 10 years, you probably get 10 to 15, no problem. But now, so then you're like, okay, well, hold everybody. Let's make sure we're making the track so that we can make it level, and not just make it level when we're all paying attention and our engineers are looking at it, but make it level when we're just assembling these things gigawatts at a time. That's sort of where our headspace is. We've got a different set of engineering challenges maybe than the work that those other teams had to do on really high quality bearings, because you've got one bearing that's your whole life. We got to make sure.
Yeah, okay, I totally get it. And so some of these challenges are not, there's kind of the in principle engineering challenge, tick. There's the modeled economic challenge, tick. And then there's the reality of getting to the modeled economic challenge. Hey, all solvable, but the work for that is always where we're at now. And it's probably a good segue, because I don't want to run over, but like what's right in front of you right now? Like, what's the critical thing that you're looking to solve in the short term, and to what end? Like where to from here?
Yeah, it's right in that space. We're building our megawatt scale pilot right now in Wyoming. We are in the middle of that fight right now to build level track and to get the wings to work and all of that. All of those, I say, get the wings to work. We know they work, but get them to work in an optimal way. It's probably a better way to put it. But I mean, I like to say, it's not fusion. These are all mechanical, electromechanical problems that engineers are very well positioned to solve, but they're unique electromechanical and mechanical problems. And so we're very much in the midst of just getting this machine to work. I think you rightly summarized. Like, we started from is there an opportunity here? If we could get this kind of thing to work, is there enough wind at this height in this configuration? What does our modeling say about, could we produce a system at low cost, and how much energy would that system produce? We've gotten all the way through that. Now it's like actually getting bolts, like the rivets, to fit in the holes that we design. And no kidding, we're putting the columns up this week. And does all that stuff fit together the way we designed it to? We need to get this one up and running. As soon as we get it up and running, we're on a race to the clock to build our commercial demonstration, which, because the IRA subsidy got voted out in the most recent administration, we need to get the commercial demo going by middle of next year, July of next year. And so we're like in that sprinting mode where get the pilot up and running, validate our modeling, right? That we've got the models, we got to validate with real world data that those models are correct, or really just how wrong they are, and then turn right around into building that commercial demo. We're not going to have it all the way built by July, but we got to start on it.
Yeah, I've probably got just two more questions just in the time we have. One of them is just a technical question that relates to, you said you've been operating at kilowatt scale, you've got to go to megawatt scale and then ultimately gigawatt. Is it just adding more of the units and doing that consistently, or is there something else that happens when you connect multiple? And then a second question I'll ask once you've got that one.
Yeah, so when we went kilowatt to megawatt, no, it was a redesign. We had, a couple of meter blade before. We're now at a 10-meter blade. That's a 33-foot blade for those who speak in feet. That's like a Cessna on its side. It is smaller, doesn't make it small. I want to be clear about that. It is still something you can handle with a forklift. It's still like accessible in this way. It fits in a container, like a 40-foot container. A 33-foot wing fits in a 40-foot container. This is all sort of, hopefully the pieces are making sense here. But I think so we did a redesign, but I think it's really important to recognize you mentioned solar and like making, billions of these little things that make bigger things. That is our scalability here was built in from the beginning too. Those 58 parts make 100 kilowatts or a megawatt or 3 megawatts or 5 megawatts. It's just the same section. We have curved sections and we have straight sections, and we need two curved sections, and the rest is just how much power out do you want. We can put in 2 or 3 straight sections or 20 straight sections, and those sections just make for a bigger power out. And that way it can be customized for different land areas. It can be customized height wise if you want to be lower for some reason or higher for another reason. There's lots of scalability here, and that's part of what has us really excited. We don't have to redesign 58 new parts every time we go to a new site. We just adapt.
Yeah, it's modular, and we haven't touched on that. It's probably a whole other conversation, so we'll park that for the moment. I do have one final question, and it's a part A and a part B, and I ask this of everyone. I want to understand what's your least favorite part of working on this whole problem and challenge, and your favorite part of working on it.
Yeah. My least favorite is the instability of being at an early stage company. If I was 25 and couch surfing, I'd be just fine. But like, we've closed funding and everybody's happy. And then like you slowly watch the clock tick and you're like, man, we only have so much runway. Like what's going to happen? And so the uncertainty there, I have 2 young kids at home, and that's just hard. It takes a toll on you. It drives you to, work hard and maybe, do fewer family things. And anyway, it is what it is. There's not much I'm going to do to change it, but that's my least favorite part. The most favorite part easily is like, look, this is a game changing tech, and I'm an impact junkie. Like I want to do something that matters. I think all of us do. And I see this as gigawatts of very low cost energy that can provide energy security in the places it's deployed. It can really change the game in terms of, as I said before, at the very top, it's like energy is our prosperity and our security. It can do a lot to address those two things, which are near and dear to my heart, and connect my whole career together from being a Marine in the early days to being an energy geek now. We all need more energy to push AI forward, to push our prosperity forward, and to ensure security at the same time.
Awesome, Neal. Wonderful talking to you guys. As I say, every so often on this show, I sometimes feel like we catch a company right at their inflection point or close to, and I feel like that's the case again with you guys here today. So thanks so much for coming on the show. I look forward to seeing how the next 6 to 9 months go, especially, and stay in touch.
Yeah, thank you. Really appreciate being here.